Hi viewers, this is Rajesh Jemlani. You are watching my YouTube channel Easy Chem by Sir Rajesh Jemlani. Today we will do an important topic of basic organic chemistry, that is isomerism. So what is isomerism? The word isomerism is a combination of two words. One is iso means same, and other is mers means units. So what is the explanation of this concept definition? The compounds having same molecular formula, if two compounds are isomers, they will have same molecular formula but different. They have same molecular formula but different properties. They will have different set of properties due to different structures. Such pair of compounds are called isomers and the process is called isomerism. So the concept is this, that there are several organic compounds which are represented by the same molecular formula but they differ in properties. Their properties are different. So why their properties are different? Because their sequence of bonding, their arrangement of atoms, their arrangement in the space is not same. So that is why they differ in properties. So isomerism is a process in which two different compounds have same molecular formula but different properties due to different structures. For example, here we have two compounds. One is ethyl alcohol and other is dimethyl ether. Both these compounds have same molecular formula. Both have 2 carbon atoms, 6 hydrogen atoms and 1 oxygen atom, but their structures are different, their functional groups are different. So here it is alcohol, it is ether. So we know that they have different functional groups. Due to different functional groups, their physical and chemical properties are different. So in this way, isomers are a pair of compounds with same molecular formula as they both compound have, but they have different structures. These pair of compounds are called isomers. Isomerism is not only possible but very common in organic compounds, and it depends upon the number of carbon atoms. As number of carbon atoms increases, as number of carbon atoms increases, the number of possible isomers also increases. It means that as the number of carbon atoms increases, we go down in the homologous series. So with every addition of CH2 group, methylene group in a homologous series or in a homologue, the number of isomers increases. For example, if we have alkane family and we have 1 carbon atom, such as methane. Methane has only 1 isomer, 2 carbon atoms, 3 carbon atoms, 4 carbon atoms, 5 carbon atoms. So up to 3 carbon atom, I mean methane, ethane and propane, they do not show isomerism. They have only single isomer. They are represented by the same molecular as well as I mean to say that they are represented by the only one structure. When the number of carbon atoms are 4, the number of possible isomers are 2. When the number of carbon atoms are 5, means pentane, the number of possible isomers are 3. Similarly, if the number of carbon atoms are 6 carbon atoms, the number of possible isomers are 5. For 7 carbon atoms, the number of possible isomers are 9. For 8 carbon atoms, the number of possible isomers are 18. For 9 carbon atoms, the number of possible isomers are 35. For 10 carbon atoms, the number of possible isomers are 75. For 30 carbon atoms, the isomers exceed more than 4 billion. More than 4 billion. So this shows that the number of isomers depends upon the number of carbon atoms. As number of carbon atoms increases, the number of possible isomers increases. So up from methane to propane, they are represented by only one structure, and they do not have any further structural isomerism, or they do not show different structures. For 4 carbon atoms, butane has 2 structural isomers, pentane has 3 chain or skeleton isomers, carbon atom has 6, hexane has 5, heptane has 9, octane has 18, nonane has 35, decane has 75, and if the carbon atoms are 30, the number of isomers increase to 4 billion. So this is what, so isomers are the different compounds with the same molecular formula and different set of properties. So here, how to find the number of possible isomers of alkanes, we will decide in the next lecture. So now we will explore what are the types of different isomers. So how many types of different isomers? So the types of isomers. There are several types of isomerism in which there are 2 major classes of isomerism. One is constitutional isomerism and other is stereo-isomerism. The basic difference in between these 2 major classifications of isomerism is that in this constitutional isomerism, the compounds differ in the connectivity of atoms, sequence of bonding. So in this constitutional isomerism, 2 compounds have same molecular formula, but they have different properties due to different connectivity of atoms, carbon atoms or different other atoms, heteroatoms which are present in the compound. Sequence of bonding, this bonding sequence may be changed, but in this stereo-isomerism, stereos means space. These isomers cannot be represented by 2-dimensional structure, but they can be. So we need 3-dimensional structure of a compound to understand this type of isomerism. In these isomers, the connectivity of atoms is the same. The sequence of bonding is the same, which is different here. So here there is no issue with the connectivity or sequence of bonding. The issue is that in these isomers, these isomers have same molecular formula, but different properties due to different arrangement of atoms or groups due to their different arrangements in a space. They differ in properties such as optical isomerism in the rotation of plane of polarized lights towards right side or towards left side. Geometrical isomers differs the same groups on the same side of the double bond, or same group or the opposite side of the double bond. In this way, these isomers have same molecular formula but different properties due to different arrangement of atoms in their space. Spatial arrangement will be different in this case. So we will do each and every type of these isomers. So isomers are mainly classified into 2 types. One are constitutional isomers, other are stereo-isomers. The constitutional isomers are further classified into 5 types: chain or skeletal isomerism. What are they? So we will do each and every type. Position isomerism, functional group isomerism, metamerism and tautomerism. Stereoisomers are further classified into conformational isomers. These isomers are not in our syllabus. Mostly alkanes and some cyclic compounds show conformational isomerism. These isomers have same molecular formula, but they have different energies due to different extent of rotation of free rotation of carbon-carbon single bond. So due to carbon-carbon, say if we have this compound, this is a carbon-carbon single bond, these are the 2 carbon atoms. So now these atoms or groups can rotate over here and there. So in this way, conformational isomers are not in our syllabus. So if we say about ethane, ethane has 3 conformational isomers. One is called skew, other is eclipse, and third one is the staggered. So staggered is the most stable and eclipse is the least stable form. Why we don't discuss here. Optical isomerism we will do separately. Configuration, geometrical isomerism we will do separately. So stereoisomers have same molecular formula but different set of properties due to different arrangement of atoms in space. They differ in properties due to left-right combination, due to up-down combination, due to optical rotation configuration. So guys, here we are with the first type of constitutional isomerism, and the first type of constitutional isomerism is chain or skeleton isomerism. These isomers have same molecular formula but different structural formula, same sequence of bonding, same connectivity of atoms but different properties, skeleton of carbon, chain of carbon. So they are the compounds having same molecular formula but different physical or chemical properties due to different skeleton of carbon. For example, here we have butane. Butane has 2 chain isomers. Butane has how many? 2 chain isomers. What are those? One is N-butane, CH2, CH2, CH3. Now this is N-butane, butane having straight chain structure, N-butane, and its another isomer is isobutane, CH3, CH, CH3. So the difference is the skeleton of carbon atom. For example, if we draw its skeletal formula, this is the first carbon, this is the second carbon, this is the third carbon, this is the fourth carbon. Here in this case, this is first carbon, this is second, this is third. At second carbon there is a branch. So this is what these isomers are differ in. So they both have same molecular formula C4H10, but their structural formula is different. The structural formula is different. This isomerism is not only possible in alkanes, but it is also possible in almost every functional group. For example, if we have an alcohol, say if we have CH3, CH2, CH2, CH2 butyl alcohol, say this is a butyl alcohol, or we say N-butyl alcohol as this chain of carbon atoms is straight chain. Now likewise we will draw its Biran chain formula, CH3, CH, CH, CH3, CH2OH. Now this is isobutyl alcohol, isobutyl alcohol. So what is the difference? The difference is in the skeleton of carbon. Skeleton, the backbone structure of the carbon chain. So these isomers have same molecular formula, but they have slightly different properties, especially physical properties. These isomers have the same functional groups, so they have different physical properties due to different surface areas. So this difference in properties is due to the different in the skeleton of carbon. So those isomers which differ in the skeleton of carbon, they are called chain or skeleton isomers. So now we will do position. What are the position isomers? Students, here we are with the second type of skeletal isomerism, that is position isomerism. So what is the position isomerism? Its a definition, how can we define it? The compounds having same molecular formula. Each type of isomers have the same molecular formula, but different properties due to different positions of carbon-carbon double bond, carbon-carbon triple bond or functional group. So these compounds have same molecular formula but different properties. They may be physical or chemical due to different positions of carbon-carbon double bond, carbon-carbon triple bond or any functional group. So examples, for example, we have 1 butane and 2 butane. The molecular formula of both these compounds is C4H6. So they both are represented by the same molecular formula, but the difference is what? The difference is that here the triple bond is the first carbon, here the triple bond is the second carbon. So this is the difference. So they have same position of triple bonds. So what are the differences in their properties? If you have studied the alkynes, you notice that one alkynes are acidic in nature, while if the triple bond is present mid of the chain, in between the chain, they are non-acidic alkynes. So the acidic alkynes have replaceable hydrogen atom. This hydrogen atom can be replaced by certain heavy metals such as silver, such as copper, or so it can also be replaced with sodium. So these alkynes are acidic in nature, while these alkynes are non-acidic. So those alkynes which are acidic in nature, showing acidic properties, also undergo substitution reaction, because these reactions in which hydrogen is replaced are the examples of substitution reactions, while these alkynes are non-acidic and they do not undergo substitution reactions. So this is what the compound is the same, the functional group is the same, but still they have different properties, and the difference is in chemical properties, and the difference is that these are acidic ones and these are non-acidic ones. Now consider another example. Here 1 butanol, so OH group is present at the first carbon, second, third, fourth. Here the OH group is present at the second carbon. So what is the difference? This is a primary alcohol, this is a secondary alcohol. When we study the properties of alcohols, so we notice that first of all these both have the same molecular formula, C4H10O. C4H10O. Both are represented by the same molecular formula, but they have different properties. What are the differences in their properties? This is a primary alcohol. When carbon oxygen bond is cleaved, when this bond undergo fission or break, so it will produce a primary carbonium. When this bond breaks from here, it will produce a secondary carbonium. So if carbon oxygen bond breaks, 2 butanol is more reactive than 1 butanol. Similarly, second possibility is that instead of carbon oxygen, carbon hydrogen bond breaks. So this bond breaks. When the oxygen hydrogen bond breaks, 1 butanol is more reactive than 2 butanol. So these are the differences in their properties. They are the same compounds, they have the same molecular formula, they have same functional group, still they have different properties, and these different properties are due to different positions of their double bond, different positions of their triple bond, or different positions of their functional groups. So here we will do now functional group isomerism. That what are the functional group? The third type of isomerism, that is functional group isomerism. Functional group isomers have same molecular formula, but different physical and chemical properties due to difference in their functional group. So these are the different compounds with the same molecular formula but different functional groups. Due to different functional groups, they have both different physical and chemical properties. Normally isomers differ in physical properties because carbon skeleton and chain due to IA, in other words we say that their surface area has changed. But here in this case, in functional group isomerism, these isomers have same molecular formula, that is common in every isomerism, but different properties, this is also common in every isomerism. This difference is due to what? This difference is due to different functional groups. So if we know that the properties of organic compounds depends upon the presence of functional group, as these compounds have different functional groups, hence their properties, both properties, physical, they have different physical and chemical properties. They will have the different set of physical and chemical properties. Examples: alcohols and ethers are functional group isomers of each other. Aldehydes, ketones, enols, cyclic alcohols, cyclic ethers are functional group isomers of each other. Carboxylic acids and esters are functional group isomers of each other. Or we say that dienes are functional group isomers of alkynes. So they are also functional group. Here dienes are what? The compounds having two double bonds, and alkynes having triple bonds. They are also functional group isomers of each other. What are enols? Where is the enol? Enol. Enol is what? The carbon chain has double bond and OH group. So en for double bond, ol for alcohol. So they are called enols. Or in other words, we say that unsaturated alcohols are functional group isomers of aldehydes and ketones. So taking first example, that alcohols and ethers are functional group isomers of each other. How? If we have ethyl alcohol and CH3OCH3. Now these both compounds have same molecular formula, such as C2H6O. Both have the same molecular formula, but they have different functional. It is an alcohol, it is an ether. So this is an alcohol, this is an ether. So due to different functional group, they have different set of physical and chemical properties. We are taking one and another example. So consider these examples yourself. Carboxylic acids and esters. Say if we have propionic acid CH3, CH2, COOH, and if we make it ester CH3, COOCH3. So now when we consider these compounds, they will have same molecular formula. How many hydrogens are there? C3H6O2. So both these compounds has same molecular formula, but here the functional group is carboxylic acid. Here the functional group is an ester. So as we know that different functional groups have different properties, hence these compounds will have different set of physical and chemical properties. Now we will do metamerism. The fourth type of isomerism is called metamerism. The metamerism can be defined as the compounds having same molecular formula but different properties due to. So these type of compounds or isomers have different properties due to unequal distribution of carbon atoms or alkyl groups around functional groups. If we have a multivalent functional group in mid of the carbon skeleton or mid of the carbon chain, such as here ether is in between mid of the chain and oxygen is divalent. Here the triple bond is at mid of the chain, and this is what an alkyne. So these isomers differ in the number of carbon atoms or unequal distribution of carbon atoms around these functional groups, or they differ in nature or nature of alkyl groups in around a functional group. So Which type of compounds show these isomerism? Alkynes, ethers, ketones, esters show this isomerism, and which do not show these isomerism, alkanes, aldehydes, carboxylic acids, they do not show this type of isomerism. Why they do not show this isomerism? Because these alkanes have no functional group, that is why this is omitted. Aldehyde functional group is always comes at the terminal position. So these isomers have unequal distribution of carbon atoms around functional groups. So aldehyde functional group come at the terminal position, hence it is not in between the chain, so there is no possibility of unequal distribution around this aldehyde group. Carboxylic acid also comes at the terminal position, that is why there is no chance of this isomerism. So here we consider an example of diethyl ether. So this is the functional group. At right of the functional group there are 2 carbon atoms. At left of the functional group there are 2 carbon atoms. So both sides, this is a symmetrical ether having 2 carbon atoms around this functional group. Now how we make its metamer? We have to skip 1 carbon from either side, from this to this side or this to this side. So I'm going to replace this CH2 group from here to here. So it becomes now this ethyl becomes methyl as one methylene group is transferred to here, and this ethyl becomes propyl as one CH2 is going to be added here. So it becomes CH3, CH2, and this CH2 comes to this side, CH2O, and the remaining CH3. Now it became, this is functional group, here there is 1 carbon atom, and here at this side there are 3 carbon atoms. So this is what, so these both have the same molecular formula but different properties due to unequal distribution of carbon atoms. Here a functional group has 2 carbons on either side. Here functional group has unequal distribution as compared to above one. Here 1 carbon at the right side and 3 carbons at the left side. So these type of isomerism in which 2 compounds have different properties due to unequal distribution of carbon atoms, such type of isomers are called metamers. In ethynes, say this is a diethyl acetylene. So this is one ethyl, this is another ethyl. Now we skip 1 methylene group from here to there. So it becomes what? It becomes now CH3, C triple bond C, CH2. Now this CH2 become here. So this is the CH2 which we have borrowed from this side. So this CH2 now became the part of this side and CH3. Now what is the difference? Here around this acetylene group 2 carbons each side. Here there is 1 carbon and here there are 3 carbon atoms. So it was diethyl acetylene, it is methyl propyl acetylene. Methyl propyl acetylene. So here it was diethyl ether, now it is propyl methyl ether. If we follow alphabetical order, methyl comes here. So this is what metamerism. So in metamerism, compounds have same functional group, same chemical properties, but they have slightly different physical properties due to unequal distribution of carbon atoms around the functional group. So now we will do tautomerism. Here is the 5th type of constitutional isomerism, that is tautomerism. The compounds having same molecular formula but different property due to shifting of proton, mainly hydrogen, from one position to other position within the molecule. It is a type of rearrangement reaction. So from one position, hydrogen is detached from one position and attached to other position within the molecule. So Tautomerism occurs when two functional group isomers exist in dynamic equilibrium, such as in keto-enol systems, such as in deuterione formation. So, in this type of isomerism, the compounds have same molecular formula, but they differ in properties due to different attachment of hydrogen from one position, detachment of hydrogen from one position and attachment on the other position. For example, keto-enol systems, say we have acetone CH3. Now its enol form or its dynamic equilibrium will be established, in which its enol form will be like this: CH2 double bond COH CH3. Now what happens? It is a ketone. It is a enol. Enol means in for this double bond, ol for alcohol. Now what happens, that this hydrogen from oxygen, it is detached from this position and it donates its electron to oxygen, and oxygen shares these electrons with this carbon. As this bond is going to form, this bond will be break. Now hydrogen remove here from this position as a positive ion. Now at this position there becomes negative charge, as this electron pair is shifted from this carbon to this carbon, as this carbon has taken electrons from oxygen, so this pair will be shifted here. Now this hydrogen detached completely from this position and attached to this position. Now this carbon bears two hydrogen before. After the addition of this hydrogen, the number of hydrogens will be 3. So here there are 3 hydrogen atoms. This, after the breakage of this double bond, it became single bond, and this single bond became this double bond. So enol has been converted into a ketone. This is a less stable form, this is a more stable form. Both of these forms exist in equilibrium. They have existence. Enol also has existence, ketone also has existence, but the equilibrium contain more extent of ketone as compared to an enol. So for the same reason, so how they are different in each other, the position of hydrogen here, from here it has been detached and it has been added here. So this is what these became two different compounds with different functional groups, hence their properties will be different. So deuterione formation, we know that there are 20 amino acids in living organism system, in humans which make more than 10,000 proteins. If otherwise there are so many types of amino acids, but we are talking about those amino acids of which proteins are made up of. So all 20 amino acids exist in deuterione formation. Say if we have glycine, CH3 CH NH2 COOH. This is a second simplest amino acid named glycine. Now glycine is an amino acid. This amino group has basic properties, and this carboxylic acid has an acidic properties. So within the molecule, proton donor and proton acceptor both are present. So what happens, that proton being acidic, it donates proton, being basic, it accepts proton. So after the detachment of proton from here and attachment to here, structure of this compound becomes CH3 CH NH3 COO. Now this oxygen bears negative charge as hydrogen has detached here without taking bonding electrons as a positive ion. So when it adds at this nitrogen bears positive charge. So negative charge here, positive charge here. This ion is called deuterione. An ion having a dipolar ion having both positive and negative charges in equal amount within the same molecule. So this ion is called deuterione. So all amino acids exist in deuterione formation due to this tautomerism. So hopefully we won't do geometrical isomerism and optical isomerism at this stage we will do in the chapter number 10 when we will do carbohydrates. So there I will explain what is optical isomerism, what is optical activity, what is chiral carbon atom, what are the geometrical isomerisms, what is the cis isomerism or trans isomerism.